Today, we want to look at volumes of solids of revolution. This is where we form a solid by rotating a region about an axis and then find the volume of that solid. We find the volume by setting up an integral, and all of our integrals so far have been based on multiplication. So we're going to use multiplication. Volume is going to be the cross-sectional area multiplied by the height. We're going to do this a second way as well. But we're going to start with this one because it fits our description. We want to do multiplication. I just want to multiply the cross-sectional area by the height, but the cross-sectional area keeps changing. Our rules for single variable calculus are that the cross-sectional area has to maintain the same shape, but can vary in size. So the single variable calculus, in single variable calculus, the shape must remain constant. It's got to be pi r squared all the way down. But the size can be variable. The shape has to remain constant, but the size can be variable. The height is going to be our delta variable. So that's what we have to write. Whatever the cross-sectional area is has to be in terms of the delta variable. So that's where things get going squish. So when we look at a slice, if our slice is getting thinner in the x direction, this is a delta y because it's getting thinner in the y direction. And then the one I actually intended to draw, where it's getting thinner in this direction, that's a delta x. So the idea is where in the direction that things are squishing. That's how the slice is getting smaller. In the dx, it's pushing left and right and up and down when we have a delta y variable. This fits into our general plan for integrating things. We want to use multiplication, but that's for when things are constant. So we assume things are constant for a small change in the delta variable. Fits in with our plan. This is the same plan we've been using ever since we introduced the definite integral way back in Calc 1. The halcyon days of Calc 1, the time before all those techniques of integration. There's actually another way. This is George Lucas making things up as he goes. There is another way that's not going to look like cross-sectional area by height until we manipulate it a little bit. So it will look like cross-sectional area multiplied by height from a certain point of view. So let's look at an example. Let's consider the region bounded by, let's say, the graph of, because I'm always going to have the graph of, y equals the square root of x, the y-axis, and the line y equals 3. Yeah, we'll send it all the way out to 9. Let's find the volume of the solid if we rotate this region about the line y equals 3. Find the volume of the solid. Formed by rotating the region about the line y equals 3. So let's draw a picture so we can see where our slice is going to be. Here's the curve y equals the square root of x. Here's the line y equals 3. Y equals 3. The intersection is going to happen when x is equal to 9. Some things that we noted. Oh, and the region that we want is the region bounded by y equals the square root of x, the y-axis, and the line y equals 3. So the region that we're looking at is up in here. I've already messed it up, so there we go. Just fill it in. We should make a note of the axis. I just noticed that my y equals 3 is all falling over. That's why I had to prop it up with this x equals 9, but you can see I used the dotted line, so it's not holding it up so well. So that's why it's slumping down a little bit. So let's label our axis of rotation. We're going to go about the line y equals 3. So this is our axis of rotation. What we notice is that our solid will not have a cylindrical hole in it because we are rotating about a boundary of the region. So let's just make a note of that, things we want to notice. Note, we are rotating about a boundary of the region we are rotating about a boundary of the region, so our solid will not have a cylindrical hole in it. So what we're going to do is take this roughly triangular shape, and we're going to rotate it about the line y equals 3. So this is going to form the other, when we look at the xy plane, through the xy plane, we're going to have circles, and the radius is going to be from y equals 3 down to this curve. And it will form another copy. There'll be another parabola up here. That goes up to 6. But we're more concerned about the region, mostly because I clearly cannot draw the bottom half of sideways parabolas. So the circle, the shape that we're going to get here will be the wide part, and it will kind of come down to a point. Here's the x-axis running through the middle of it, and the y-axis will be at the face of it. And so we'll get this shape. And for some reason, we want to know the volume of this shape. We can get an upper bound on this volume because this would fit inside of a cone with a radius of 3 and a height of 9. So, but we know it's going to be smaller because a cone would have a straight line going from 0, 0 to 9, 3. But this one is concave down, so it's bent inside. So it's going to fit inside a cone. So our volume, so we should also note volume should be less than the volume of a cone, which is 1/3 pi r squared times h. So 1/3 pi times the radius 3 squared times the height, which is 9. The volume of a cone. So let's imagine how we're going to slice this up. We're going to slice this up in a dx way. So we're going to slice it vertically. If we take vertical slices, the vertical slices will be shaped like circles. Vertical slices will be circles. So if I take, make sure I give myself enough space. If I slice vertically here, and imagine this slice getting rotated around, I'm going to create a circle. And the part inside the shaded region is going to be the radius of the circle. So there'll be the rotated part of the circle above it. So when we go to create the volume of the slice, we'll have the cross-sectional area. Since the vertical slices will be circles, the cross-sectional area will be pi r squared. And my delta variable is going to be delta x. We should note that the slice intersects a point on the graph. And so we have to label our x and y. And then we have to look at our slice, which is getting a little smeared here. And we have to label the radius. Now, the radius of the slice is always from the axis of rotation to the end of the slice. Anything that you're going to call a radius in any of these problems has to be measured from the axis of rotation. The rotation is what causes a radius. So it's the 0 for the radius is always at the axis of rotation. So here's the radius. That's going to be this tiny radius here. Everything started getting smaller, and now I can't write radius, but it's the radius. There. We just need to write the radius in terms of x. What we notice is that the radius is a vertical thing, so it's going to start off in terms of y. So note that the radius is vertical, so it starts off in terms of y. So the radius is going to start off in terms of y, and then we'll use the function to trade y for x. So it starts off that the radius, since the radius is this piece from 3 to the function, and from the function down to the x-axis is y, the radius is 3, the total, minus y, the piece. So the radius is 3 minus y. But we need a function of x. So we use the function y equals x squared to write the radius in terms of x. Sorry, y equals square root of x to write the radius in terms of x. So the radius is going to be written as 3 minus the square root of x. Now I have the radius in terms of x. I have delta x is my delta variable, or x is my delta variable. So I'm ready to put this all together into the volume of the slice. So the volume of the slice is pi times the radius, which is 3 minus the square root of x squared times delta x. Now I'm ready to move this on to the total volume in a definite integral. So our total volume, I'm just going to label it V total. There's going to be the Riemann sum. But I'm just going to go directly to the definite integral. I've got the thing that I'm going to be integrating. So I'm just going to write my definite integral. I'm going to factor out the pi. I'm going to integrate 3 minus the square root of x squared. In the definite integral, the discrete delta x becomes the continuous dx. And we integrate over all the values of x that we're using. And in dx, x goes from 0 to 9. Like I mentioned before, we normally don't write x equals 0 to x equals 9 on our definite integral, but we want to remind ourselves the connection between the dx and the variable that's in play when we integrate, the interval. Writing dx here says that this interval needs to be an x interval, so let's make sure that we're writing an x interval. This is like writing 1x when you do 5x minus 4x. You write 1x when you're starting off. Then further you go, the less you need to rely on writing 1x. You just start reading x as 1x, and you don't write that as much anymore. This is an integral that we could do by hand, or we could just grab the calculating machine and do pi, math 9 for integral, and we'll integrate 3 minus the square root of x squared. So parentheses 3 minus the square root of x, close the courtesy parentheses, close the thing that I'm squaring, and then square it with respect to x from 0 to 9. And we get 42.411, we'll call it. This might be some integer multiple of pi. Let's see if the calculator can tell what integer multiple of pi is. Get rid of the pi. It looks like it's going to be like 13.5 pi. This looks like it's been rounded off. But you wouldn't want to write 13.5 pi. If you're going to write decimals, write your decimal approximation. Include pi in the decimal game. So you could write 27 pi over 5. Over 2, sorry. That's probably what it is. Based on the fact that there are 3s and 9s running around, there's a 1/2 power, and I don't know. That's just what it looks like to me. But you wouldn't want to write 13.5 pi. Don't write a decimal and then stick pi on the end of it. That just looks weird. I don't know. Maybe there are some people that maybe that's going to become acceptable in the future, but it's not right now, and it never will be with me. So I don't know. Maybe that's just a pet peeve of mine. Any questions? Now we need to play the variations game. There's certainly the implied variation that I'm going to change how we slice things. And there's also since I'm calling out specifically, we're rotating about the boundary of the region. So what happens if we negate that? What happens if we rotate about not a boundary of the region so that our solid does have a cylindrical hole in it? What's going to happen? All right, so let's do that. Any questions before we go on? Just going to move the radius and see what changes. It's week 10, by the way, and next week is spring break. So there's going to be a week off. I know everybody's thinking, that's the week I'm going to use to catch up. I don't know, maybe you already are caught up. I don't know. Let's do the same region. About the line y equals 5. So I want the same region, but now I'm going to go about the line y equals 5. Here we're going to note that the axis of rotation is not a boundary of the region. The axis of rotation is not a boundary of the region. The solid will have a cylindrical hole in it. So let's sketch the region and the axis of rotation and imagine what the slice is going to look like. So there's our region. It's going to be this triangle in the upper part. Make sure to shade it vertically this time, because I'm still going to use a vertical cut. But the axis of rotation is going to be up above this at 5. Now we're going to do the same thing. We're going to draw a slice in the region. Well, actually, we're going to get, when we rotate this region, notice that the axis is around, the line y equals 5 is the axis about which we are spinning the region. So the region is 2 units away from the axis of rotation. So this point is going to rotate to a point 2 units above the axis of rotation. That's going to be the base of the region. So when I look at a slice that was a circle before, I had this slice that rotated to a circle. That slice is going to have a hole in it, and the other end of that slice is going to show up way up there. So there's a 2 unit hole, a 2 unit radius cylindrical hole in the center of our solid. So this actually happens way up here at y equals 7. So when we go to find the air, so the slice that we're getting is not a solid disk. The shape of the slice now is that of a washer. So the slice is not a disk with a pi r squared area. The slice is now a washer. That's a disk with a hole in it. So the slice is now going to be a washer, which is a disc with a hole in it. And so what we're going to have is two radii. So we'll have an outer radius and then the inner radius. And then this part that's getting rotated, that's what we're looking at labeled in the graph up here. So a washer has two radii. There's going to be an outer radius and there's going to be an inner radius. Because we just take the area of the big circle and subtract the area of the little circle inside. And so I'm going to use a capital R for the outer radius and a little r for the inner radius. And I will, in speech, refer to both as R. This is because we have bad habits. Notice that this still happens at 9. This is all still happening at 9. So what we're going to do is we're going to find the volume of the solid. All we're going to end up doing is subtracting the cylindrical hole. The pi little r squared is going to be a cylindrical hole. That's just this rectangle rotated around the line y equals 5. We want this distance to be the same so that we can multiply. But this orange distance here, it keeps changing size. So we're going to assume it's the same for a small change in x like we always do, because this is the way. We're going to go in and label the points x and y on the graph, on the axes, like we always do, to remind ourselves where we are. And then we're going to go into the picture and label what the inner radius and the outer radius is going to be. We're going to remember that the radius is always measured from the axis of rotation. The radius is always measured from the axis of rotation. If r equals 0 is not the place where you're around which you're rotating, then you're not looking at a radius. You don't measure the radius of your wheel from the edge of your rim, because that's not the point around which your wheel rotates. So there are going to be two radii from the axis of rotation to the near end of the slice. So from the axis of rotation to the near end of the slice, that's going to be the little r. And then from the axis of rotation to the outer edge of the slice, that's going to be our big R. Here's the outer edge of the slice. Now we're in the same situation we were before. The volume of the slice is going to be the volume, the area of this washer, which is just a disk with a hole in it. So pi r squared, pi times big R squared minus pi times r squared times delta x. It's going to look like pi r squared times delta x minus pi times r squared times delta x. But notice that each of these two terms has a pi and a dx. So we're going to write this as pi times the difference between big R squared and little r squared. and then just have one delta x at the end. Then afterwards, we'll notice that all we're doing is subtracting a cylindrical hole or subtracting from a cylinder. Anything that we call a radius is going to be measured from the axis of rotation. Notice that the near end of the slice is always 2 units away from the axis of rotation, because the axis of rotation is 5, and the upper boundary of the region is at y equals 3. So that's always 2 units away. So the little r is constant. The big R is measured from the axis of rotation to this point on the function. The axis of rotation to the x-axis is 5. The distance from the x-axis to the function is y. So big R is 5 minus y. But this is a delta x problem, so I have to trade my y for an x using the function, just like we did before. So the big radius will be 5 minus the square root of x. I have an expression for the big radius in terms of x. I have an expression for the little radius in terms of x. It was constant, so that was pretty easy. Now I just need to put this all together into an integral, which I'll write as the total. I think I'm going to stop pronouncing this as the slice and the total, because YouTube is going to try to translate that into a word and it's not going to recognize it. I've also noticed that the YouTube closed caption algorithm doesn't really recognize letters very well. All right, let's press on. Let's factor out the pi like we did before, and we're going to integrate r squared minus r squared. Big R squared is 5 minus the root x. That has to get squared because it's big R squared, and little r squared is just 2. And then the delta x, the discrete delta x, becomes a continuous dx as the slices get infinitely thin. We're integrating in terms of, we're integrating an x integral, so we have to look at all the x's for which we have a slice, and the x's go from 0 to 9. We could integrate this by hand by multiplying all this out, but if I said round your answers to the nearest, to 5 significant figures, that's when calculator comes into play. So a calculator shows up. It's kind of like Clippy. Every time I hold my calculator at this angle, I imagine it showing up like Clippy in Microsoft. It's like, oh, it looks like you're doing an integral. Can I help? And then you're like, oh yeah, calculator. So I'm going to do pi times the math 9. Ooh, I need a lot of parentheses. So I need parentheses 5 minus the square root of x squared minus 2 squared. Could have just written 4, I guess. With respect to x from 0 to 9. Close parentheses. $155.51 to 5 significant figures. This is probably some fractional multiple of pi. I don't know if we'll be able to see what it is if we divide out the pi. Maybe 49.5 pi. Probably 49.5 pi. Seems reasonable. So what's 49.5? 99 over 2. Maybe. So This seems like a lot of work to get the volume of a solid that we very suspiciously want the volume of. But remember, it's not about finding the volume of this solid. It's about thinking in terms of integration as multiplication, cross-sectional area multiplied by height. And then it's about doing analytic geometry to write the cross-sectional area as a function of the delta variable. Any questions? So here are some questions moving forward. What if the axis of rotation is below the x-axis? So what if we're rotating about the line y equals -2? What would the shape look like? But more importantly, how would we set up the two radii to calculate the volume? And what's this other slicing method you talked about? So those are some things that we want to consider moving forward. Any questions? All right. That's going to do it for today. Everybody, welcome back to the new week. Everybody have a good day. I'll see you tomorrow, and thanks for playing.